Alright, so today I'm gonna be talking to you about problem 3 of the Ossenbrugen section 5.3 section. And if you recall, we had to build a wastewater aeration tank underground. So if you look at here, this is our figure 5.45, the one that we had to follow. And it gives us that the cross-sectional area is going to be a square cross-sectional area of value of A. And since we have a square cross-sectional area, that means our length equals our width. And since they're both the same side, in order to get A, each side is going to be equal to the square root of A. Then we have our tank of area, of some depth equals to D. And then we have our ground slabs here in the bottom, and everything here on the side is going to be our walls. So part A said to determine a cost function given these parameters here. So we built our cost function in terms of our control variables A and D, because that's what is asked for right here. We set up our function by looking at first looking at the constant parameters. If you look at the excavation cost is going to be in terms of some volume. The same thing for installing the ground slabs and the walls. They all depend in some area or some volume, for the exception of the reinforcing steel. So that's going to be constant no matter what. So then our first part for our function is going to be $10,000, and that's for the steel. Then we look at how much is going to cost to excavate this thing. That's the first step. So we know that our depth is going to be equal to D, and then in order to get the volume, we have to multiply by the area of this whole square right here, and we know that area is going to be equal to A. So then the volume, which is is going to be A times D. That gives us the volume. Now we're going to have to multiply how much it's going to cost to excavate this thing. And if you notice here, the excavation cost is per yard cube, but we're working on feet. Oh, with foot, I'm sorry. And as we change that to foot cube, we're going to have 23 cents per foot cube. And that's what's going to cost us to excavate this tank. Now we look at how much it's going to cost us to install the ground slabs, and that's this bottom here. And if you notice, that's going to be in foot square or feet square. So then we know that the area here at the bottom is going to be A. So then it's going to cost us $4 times the area A to install this ground slabs. Next, we look at the walls. So if you notice, the walls is going to cost $2 with 60 cents to do the formwork, and $3 with 20 cents to put the cost in place, to put it in place. So we could just simply add that. We could add those two prices. So that's 2.6. I'm going to do that here in the bottom. So that's going to be 2.6 plus 3.2. Now, let me erase this. Okay, so that's going to be 2.6 plus 3.2. And we know that we have 4 different walls here. So that's times 4 walls. And now we need to figure out what the area is for each of these walls. Because the units are in feet square. So we know that the length is going to be D, or our depth. Now we need to figure out what our width is. And as we mentioned earlier, that's going to be the square root of A. And we have nothing else that is part of this. That's gonna affect the cost. So this here is gonna be our cost function. So we move on to the part B, where now it tells us to draw two isocost lines of $50,000 and $100,000. So now we know that C is going to be equal to 50K. C1 is going to be equal to 50K, and also C2 is going to be equal to 100K. So if we look back at our isocost, at our cost function, here, now we know that this equals 50,000K and 100,000K. So when we plug it in, we know that 50,000, which is our budget, equals to the 10,000 to install this steel, plus the cost of excavation, which is going to be 0.23 times our area times our depth, plus the cost to install the ground slabs, which is that's 4 times A, plus the cost to install the walls, and that's going to be 23.2 times D times the square root of A, and that's just multiplying 2.6 plus 3.2 times 4. Alright, so now we have two variables. So we could find one in terms of the other. I chose to find for D because it's much simpler. So then we have 40K in this side when we subtract 10 of 50. It's going to be equal to D times 0.23 times A plus 23. Alright, so then like I was saying, that's going to be 23.2 times the square root of A, because I factor out D, and then we have plus 4A, plus 4A. So now it's really easy to just solve for D, and I do that by simply moving everything to the left side. So we're gonna have 40K minus 4 times A divided by 0.23A plus 23.2 times the square root of A. So that's our function D in terms of A. And that's by holding our budget constant to $50,000. Now we do the same thing for $100,000. The only thing that's going to change is this value here. So we know that D in terms of our function A is going to be equal to, this time is going to be $90,000 minus 4 times A divided by 0.23 times A plus the cost of our walls, which is 23.2 times the square root of A. And I notice here this should be just A. Alright, so now we have our function D in terms of A for both cost $50,000 and $100,000. Now we graph those two functions, D1 and D2. So this is D2, this is D1. And we get a curve like this one. And you can graph this in your calculator or Wolfram Alpha. So this here, that line, this green line right here, is going to be our cost when we hold it at 50K. and this axis here is going to be A, and this axis here is going to be B. On the second curve, this red one here, is when we hold our cost at $100,000. So we have a fixed budget of $100,000 or $50,000, and we want a cross-sectional area of 200. We know that when we hold our budget to $100,000, we're going to waste approximately $125. 125 feet is going to be our depth. And then if we hold our cost at $50,000 and we want the same cross-sectional area, our depth is only going to be approximately 50 feet right here. So that was our isocost function. Part C says determine the maximum tank volume when our cost is going to be held at $50,000. So that's when we know that volume is going to be equal to our depth times our area, and we have to maximize that. We have to maximize our volume. So to maximize our volume, we take the derivative of B, and since we solved our cost functions in terms of D, it's much more simpler to just plug in D in here in terms of A. So we're going to solve in terms of A, and we know that our area times going to be 40K. Yeah. Alright, sorry. So then we're going to multiply our area times our function D in terms of A. And we're going to take the derivative of that in terms of A. So when we do that, we're going to have, you take the derivative, you could do that through Wolfram Alpha, or you could do crazy calculus. We're going to end up with negative 17.39 times our area to the power of 3/2 minus 2,631.32 times area plus you're gonna have plus 8.77 times 10 to the 6, and all that divided by the square root of A plus 100.87 square times the square root of A. And since we want to maximize it, we're going to set that equal to 0. So once we set that equal to 0, we could just solve for A. So when we solve for A, let me erase this. So when we solve for A, we get an area of 2,504.8 feet square. So when we plug that in back into our function here, we get a depth of 17.26 feet. So what this means is that with $50,000, our maximum volume is going to be achieved by a cross-sectional area of 2,504 feet square and with a depth of 17.26 feet. And thank you, and I hope you enjoyed this.